All right. So yeah, thank you for inviting me to speak today. So yeah, the talk today will be about a result on the BMS supertranslation charges that comes from work that I've completed during my PhD with Karthik Prabhu and Juan Valenti Kroon. So I gave the talk a few times before, but the beginning of the talk today will be a bit different from the ones I've given before, just because I decided to start with I guess, a long introduction on asymptotic symmetries and the motivation for the work. So, hopefully throughout the talk, everything will be understandable, but also I'm happy to take any questions during or after the talk. Um, so before I talk about the conservation of the charges, I do want to start by giving a bit of a motivation for why asymptotic symmetries and the charges are relevant for a large section of research in both classical and quantum gravity. So as you may know, there's a lot of interest in GR in studying the asymptotics around isolated objects, which you can think of as representing abstractly astrophysical objects. And in the 60s, there was a lot of interest in describing these kind of isolated objects, particularly describing solutions of Einstein equation with vanishing cosmological constant. So from this period, we have two very influential approaches to asymptotics that introduce this idea of what it means for a spacetime to be asymptotically flat. And obviously, one of these approaches is the conformal approach, which was introduced by Roger Penrose, which, as you may know, it gave a geometrical definition of asymptotic flatness, which is inspired by the conformal compactification of Minkowski spacetime. So just as a reminder, we're probably all familiar with the stereographic projection, which allow us to compactify R2 into S2. In the case of a four-dimensional spacetime, the idea is the same. So you can compactify R3 into S3. So for the flat four-dimensional Lorentzian space, which is the Minkowski space, that means that we can embed that into this four-dimensional cylinder. And the area in the cylinder here, which is shaded, you can think of as representing the entirety of Minkowski spacetime. So specifically, it shows the causal relation between points on Minkowski, but it contracts the length or the distance between these points. And from this, we also get the diagram, the conformal diagram of Minkowski, which shows the different parts of the conformal boundary, which, as you may know, it can be split into different regions. So we have past and future time-like infinity, past and future non-infinity, and we also have spatial infinity. So the idea, asymptotic flatness in Penrose is basically tells us that spacetimes are asymptotically flat if the null conformal boundary resemble what we have here in Minkowski. And historically, like the focus on non-infinity is because it's the region of space we're interested in if we want to describe gravitational radiation. But obviously, we also have other definitions of asymptotic flatness, like the ones by Ashtikar and Hansen and Romano, which also give you a notion of asymptotic flatness at spatial infinity. Okay, but the main point of the talk is to discuss asymptotic symmetries and charges. So the framework which is largely used in the setting is the one which was introduced by Bondi, Matzner, and Saka and Vandenberg. And in this framework, the notion of asymptotic flatness is a coordinate-based description, where you say that a spacetime is asymptotically flat if at large radial distance, the metric can be written in this form. So in this description, we're using the Bondi coordinates, which are adapted to future non-infinity. So we have r, which is the radial coordinate. We have u, which is the retarded time. So it allows us to move along future non-infinity. And I am also using xi and xj just to denote some coordinates on the sphere. Okay, now you obviously recognize at least some part of this metric because it shows the flat Minkowski metric written in Bondi coordinate. But we also have some other terms here, these terms that contain information about gravitational radiation. So specifically, these terms are related to the asymptotic shear, the Bondi mass aspect, and the angular momentum aspect. And in the context of asymptotic symmetries, we usually ask what sort of transformation would preserve this expansion of the metric. And by preserving the expansion, we just mean that we want to describe transformation that preserve this fall-off behavior of the metric. So in practice, we would be looking for some vector xi, which can be expanded in terms of our coordinate basis in this way. And explicitly, you can solve for this transformation on future null infinity. And you find that it's parameterized by this function t and this two-dimensional vector y. And you can think of these two as a parameter of the infinite dimensional group, which is known as the BMS group. So the part of the vector, which is this part here, is the one which is responsible for what we call supertranslations, because in null infinity, you can show that it imposed a translation of the retarded time by specifically this function t, which is a function of the angular coordinates. And since it's a function of angular coordinates, that means that we have an infinite number of these kind of translations. We also have, this other part of the vector, which is basically what generate the Lorentz transformations. So in the end, you get this, you can show basically that the BMS group has a structure. So it's a semi-direct product of the Lorentz group with the supertranslation group. And this structure is familiar because it's exactly like the structure of the Poincare group, which is the isometric group for Minkowski, which also can be written as a semi-direct product of the Lorentz group. But in this case, we replace this supertranslation part with the for the translations. Okay. So hopefully this gives you just a good summary of the BMS group. But now to come back to the point of the talk, which is the conservation of these symmetries, or more specifically, the charges associated with them. So there are 2 points that I want to make here. So first, how we actually define the asymptotic charges associated with the BMS group, and also why we are interested in the conservation across spatial infinity. So let me first start with the first point. So the motivation for introducing charges associated with symmetries really comes from Noether theorem, which tells us that if you have symmetries of a physical system, that these should be associated with conserved quantities. So if the asymptotic symmetry group in this case is this BMS group for asymptotically flat spacetime, so we would naturally expect that there is some charges associated with these generators. However, in the case of these conformal, asymptotically flat spacetime, the situation is a bit more subtle because at null infinity, generally what we find is that actually these charges are not going to be conserved in the usual sense. The reason is that we're gravitational radiation, we know that it escapes through null infinity. So instead of having some strict conservation laws for these charges, what we get is we get some flux balance law. So if you try to take some 2 cuts of null infinity and you evaluate the charges at these 2 cuts, the difference between them would basically be related to the flux of radiation through null infinity. And historically, they can think of kind of the first quantities that were associated with the BMS group were the Bondi-Sacks energy and momentum. So these correspond to the translation part of the BMS group. So explicitly, you can obtain these charges by taking the 0 and the first spherical harmonic of the supertranslation parameter. So it's these basically where the L goes for 0 and 1. And you integrate these against the Bondi mass aspect over some cut of null infinity. And these give the Bondi mass and the 3 components of the Bondi momentum. But as I said, in these charges, you don't expect them in this case to be conserved. And actually, their evolution in retarded time, so along null infinity, they obey the Bondi mass loss formula. Okay. Now, the question in this case is how we define also the charges which are associated with the full BMS group. So if you try to kind of follow the usual logic from Noether theorem, we actually find that at null infinity, the full BMS charges in general are not going to be integrable. But over the years, there was kind of different approaches on how one can define these charges. So these are some of the references that you can look at for this. But in this case, the list is really not exhaustive. So you probably can find other areas or papers in the literature that talk about this. But at least for the purpose of the talk, I will be just referring to the Wald-Zubris formalism, since it's the framework on which my results is based on. So the main idea of this description is to take the Noether charges, which are associated with the Xi, which is the generator of the BMS group, and add an additional boundary term, which is defined so that basically it removes the non-integrable part of the charges. So this boundary term is defined intrinsically on null infinity. And this leads to a well-defined definition of the BMS charges. And using this description, we get this general definition here, which is associated basically with the asymptotic charges associated with the BMS group. So in this parts here, I have like this beta term, which is related to the supertranslation parameter and also the Lorentz parameter. And then the other parts are related to also the Lorentz parameter. And specifically, we have super momentum part of the charge, which in this case is the one associated with the supertranslation parameter t. And we also have another part, which is the angular momentum charge, which is associated with the Lorentz generators. Okay. Now, the title of the talk is saying I'm talking about the conservation of the BMS supertranslation charges. And I'm talking here in this case about the translation not on null infinity, but at spatial infinity. So for the rest of the talk, I will be just focusing on the supertranslation part. So effectively, I'm basically setting the Lorentz parameter of the charge to vanish. And if you try to take this expression of the charges and you write it in terms of the Newman-Penrose gauge, which is again just another gauge in this case adapted to null infinity, you get this expression here. So this expression have the first part is this function p, which you can show that it's related to the Coulomb part of the Weyl tensor. So basically, it's just the contraction of the Weyl tensor with the different Newman-Penrose null tetrad. And then we also have this other term here, which is related to the bonding use and the shear. And you can show that specifically this kind of contraction between the shear and the use at future null infinity, it can be written in terms of the spin connection coefficients of the Newman-Penrose formalism. So specifically, it's related to the sigma and the mu and the gamma. Okay. And you can write similar kind of expression for this also at past null infinity. So this, is supposed to give you a very quick introduction into the BMS charges. Now, I also want to say a few more words on the second point that I mentioned a while ago, which is why are we even interested in the conservation of these charges across spatial infinity? Okay, so now, as I mentioned earlier, when we are studying asymptotically flat spacetime, we typically have two null boundaries, which is a past null infinity and future null infinity. And you can think of these as corresponding to incoming and outgoing radiation. And when we define quantities like the BMS charges, these are usually defined intrinsically on the boundary. So that means that we have two independent definitions of these charges at past and future null infinity. And in general, we don't have like a relation between these charges. But if we want to understand physical processes like gravitational scattering, we would like to relate the data, which is defined at past null infinity, to the ones that are future null infinity. So essentially, we would like to know whether there's some notion of conservation that connect the charges defined on these two boundaries. And this is really where the matching across spatial infinity comes from, because the region of spatial infinity is obviously it's a part of the conformal boundary which connect these two different sets. So if we want to compare the charges, which are defined with square minus and square plus, we need to understand how the fields that appear in the definition of the charges, how they behave as we go take the limits to spatial infinity. And one of the reasons also this problem became like a very active topic of research in recent years is due to this paper by Strominger on the role of the BMS symmetry group in gravitational scattering. So the basic idea is the following. If we do assume that we have some relation between the BMS charges at past and future non-infinity, then this relation you can think of as a global symmetry acting on the gravitational scattering process. So specifically, remember that in scattering theory, you describe the dynamics of what's happening in the bulk of the space using what is known as the S matrix, which is an operator that map incoming states defined at past null infinity to outgoing state at future null infinity. And this paper shows that if the BMS charges are conserved, then the global symmetry group, which is generated, must also be a symmetry of the S matrix. So this tells us that the S matrix should be invariant under BMS transformations. So in a way, you can think of this basically as somehow of a constraint on the scattering process. So obviously in this picture that tells us that the conservation of the BMS charges is important because it suggests that there is some connection between asymptotic symmetries and gravitational scattering. Another reason why the study of this asymptotic charges and symmetries is important because of the relation to gravitational memory. So remember that I said earlier that on null infinity, the BMS charges are not conserved. And the difference between charges evaluated at two cuts is related to the flux of gravitational radiation. So physically, this means that if we have some gravitational radiation passing through null infinity, this means that it will leave a permanent change in the value of the BMS charge, which you can think of as manifesting as a permanent displacement in the gravitational wave detectors after the gravitational wave pass. And this is exactly what the gravitational memory is. So again, in this case, you see that the asymptotic symmetries are connected to an observable, which is gravitational memory. So overall, kind of these results basically tells us that, this assumption, and they all rely basically on the assumption that we have some conservation law that holds at spatial infinity for these charges. And really this brings me to the main point of the talk, which is whether we can actually expect this conservation to hold in a general gravitational scattering process. And specifically, since in my work, the focus on an initial value problem, the question is what would be the initial data conditions that are required for this kind of matching to hold at spatial infinity, okay? Any questions? Hopefully it's fine. Okay, so yeah, before I go into the more technical aspect of the talk, I also kind of just want to briefly say how I came to work on this problem of the matching. So when I first started looking at this question, I kind of began with linear fields, so in particular spin 1 and spin 2 fields on the Minkowski background. And at the time, there was a quite substantial amount of work on the matching problem already. So I was kind of entering a topic that has already been studied quite a lot. But I think one aspect at the time which was missing from the discussion is this initial value perspective. And this is, as I said, it's important because it's the way to test whether this matching can hold for a large class of spacetime that satisfy Einstein field equations. And in some sense, I was also very lucky because during my PhD, I've worked with Juan, who obviously have a lot of expertise, studying the initial value problem in GR, and specifically using Friedrich's conformal approach, which also turned out to be a very well adapted approach to studying the behavior of fields near spatial infinity. So overall, I think it was like a win-win for me in this, at least for looking at this kind of problem. But yeah, so for the rest of the talk, I want to briefly present how we used Friedrich's framework to study the matching of BMS charges in the full GR setting. So yeah, that means that at least at the beginning, what I need to do is I just need to introduce the Friedrich's formalism. So I kind of like to think of Friedrich's approach in this way. So you think of it as a conformal approach, which was introduced again, this is just my perspective, to solve two problems in the conformal GR setting. So the first, which is the fact that if you consider conformal transformations like the one we introduced earlier for Minkowski, you would generally obtain a singular structure at spatial infinity, specifically if you consider spacetimes with non-vanishing mass. So the solution for this in Friedrich's formulation is to introduce a blow-up of spatial infinity, which I will discuss with more details in a bit. Then the second problem is the fact that if you start with a spacetime satisfying Einstein vacuum equations, and if you consider some conformal transformation, you can show that this implies a singular equation for the conformal Ricci tensor on the conformal boundary. So effectively, that means that we cannot use the transformation law as an equation for the metric components on the conformal boundary. So instead, in Friedrich's formulation, we work with these equations, which are known as the extended conformal field equations, which you can group in this way. So you have some equations for the background fields, which are just the frame fields, the connection coefficient, and the Schouten tensor. We also have some equations for the gauge fixing, which are basically these equations. And we also have equation for the gravitational field, which is just the Bianchi equation for the rescaled Weil tensor. Okay. So this is a very brief introduction to this equation. I don't think the details of the construction of this will matter so much for us. So I chose not to really bore you with the details. But now I just want to come back to this blow-up procedure that I mentioned, which, as I said, is supposed to resolve this singular structure at spatial infinity. And this really also leads to one of the main structure in Friedrich's formulation, which is a cylinder at spatial infinity. So in Minkowski spacetime, what we get is this picture. So rather, than having this point I0, which connect past and future null infinity, we have this cylinder, which intersect scri minus and scri plus in these two spheres, which are known as the critical set. And the way this cylinder is introduced in Minkowski is quite simple. So you start with the Minkowski metric in spherical coordinates. You introduce a coordinate transformation. And then you also introduce a conformal transformation, where in this case, the conformal metric is related to the original metric by this conformal factor, which is just rho multiplied by 1 minus tau squared. Then if you do this transformation, what you get is that the conformal metric can be written in this way in terms of the new coordinate. And then we also see, like, from the expression of the conformal factor here, that it gives you the conformal boundary, which is the point where the theta is equal to 0, and this conformal boundary can be divided into subsets. So the first one is the past and future null infinity, which correspond in this case to tau equal to plus or minus 1. And then we also have the critical sets where the cylindrical coordinates at this point rho is also equal to 0. And the last is I, which is a cylinder at spatial infinity, where rho is equal to 0, but tau is not equal to plus or minus 1. So as I said, in this case, this basically just introduces blow-up of the case. And the reason you can show that this cylinder is a cylinder, because you can see that in here from this metric that the intrinsic metric on this set will be just a cylindrical metric. Okay. Now the question is, so this is on Minkowski spacetime. The question is how we can generalize this construction to asymptotically flat spacetime. So in this case, this blow-up, is initially introduced on a space-like hypersurface because, as I said, Friedrich's formulation is an initial value problem formulation of the field equation. So generally, we would introduce a 3+1 decomposition of our spacetime. And in this case, when I'm saying like we're wanting to introduce this blow-up on an asymptotically flat spacetime, so in this construction, what I mean by asymptotically flat spacetime is that it's basically the development of some asymptotically Euclidean initial data. And, asymptotically Euclidean data simply means that on the initial hypersurface, the geometry far away resemble the geometry of an Euclidean space. But in the conformal approach, instead of describing this behavior by going infinitely far away, we reformulate this idea using a conformal compactification, as I said earlier. So this is, very similar to the stereographic projection, where you add one point to your plane so that it can be mapped to the sphere. So in that same spirit, so what you do, you start with some initial hypersurface. You assume that you have some asymptotic end. All of these asymptotic ends, or each of them, in this case, can be mapped to a different spatial infinity point in the conformal initial data, okay? So basically, this definition, what it does is introduce a point compactification, which is exactly the kind of conformal transformation that also appear in Penrose's definition of asymptotic flatness. So now, we have this kind of notion of asymptotic flatness from this point of perspective of like the initial data. What we want to do is we want, as I said, to introduce this blow up of Friedrich. So what we do in this case, you can start from this definition and take some initial hypersurface, and you assume that in this case, just for simplicity, you have one asymptotic end. According to this definition, this asymptotic end can be mapped to a spatial infinity point on a conformal initial hypersurface. Then the classical way you can obtain a blow up of this point is to replace the point I with the space of direction at I, and this would introduce a blow up of I to a two sphere. But in Friedrich's formulation, the point I is actually replaced by a subset of the normalized spin frame, which has a structure group SU2C. So I will explain this a little bit later, but anyway, in this description, basically what you get is you get that the point I is blown up to a three sphere, and you can think of this extra dimension as just a reflection of the freedom you have in choosing the phase of the spin frame. So then if you do a quotient by U1, what you get back is you recover the usual two-sphere blow-up of spatial infinity, okay? Now, to do this kind of blow-up more explicitly, so, think of this, you have some kind of ingredients that you need to start with. So the ingredients are the following. So you need some normalized spin frame at I. You need a choice of a time-like vector field, which in this case, we choose to be normalized in this way. And you need some SU2 matrix, SU2C matrix, on two real parameters, tau and rho. Now, in order to put these ingredients together, what you do is you take your frame at I, and then you consider its transformations by t. So what you get is you get this transformed frame, epsilon at. So now we have some transformed frame. It's still at I. What you want to do is we want to extend this to a neighborhood of spatial infinity on the initial hypersurface. So what we do is we take a geodesically convex open ball at I, and you extend these frames in a neighborhood of I by parallel propagation along geodesics. So in this case, if the parameter along the geodesic is rho, then the spin frames, which are in this case defined in a neighborhood of spatial infinity, will be parameterized by rho and by our transformation, which is the SU2C transformation. Then the next step is we want to lift these frames off the initial hypersurface. So what we need to do is we need to consider some propagation law. In this case, we consider some propagation laws along conformal curves, which are known as conformal geodesics. So these are basically a pair of a curve, x tau, and one form that satisfy some ODEs. So it's not important, at least like the equations at the moment, but the important thing is so you have some parameter also along this curve. So that means that if tau is a parameter, then what you get is you get basically your spin frame, which is defined on the space-time, will be parameterized by tau, rho, and the t. Okay. Now, there's also one thing, I guess, to explain here, which is why we choose this t to be an element of SU2C. So in this kind of framework of doing this kind of 3+1 decomposition, from the point of view of spinners, what we actually have is we have two notions of inner product in our, spinor space. So what basically we have the usual inner product, which is defined in terms of this epsilon spinor. And we also have a notion of an inner product, which is a Hermitian inner product, which is defined in terms of the time-like vector that we have in our space. And usually, if you want to preserve the usual inner product for spinor, what you consider is transformations that are SL2C. But in this case, we want to preserve two inner products, both the usual inner product and also the Hermitian. So in this case, the kind of transformation that preserve these are the SU2C transformations. Okay. Okay, so then this basically construction tells us that, if you start with a choice of a spin frame, and if you have a choice of tau and rho and t, this allows you to propagate that spin frame into the space-time. So in this case, we can basically consider that our conformal manifold is this 5-dimensional fiber bundle with coordinates tau and rho and t. And basically, these tau and rho and t, they basically satisfy these conditions. So and in this conformal manifold, we can define kind of similar sets to what we had before of the conformal boundary. So we have past and future null infinity. We have the critical sets. We also have the cylinder at spatial infinity. And in this case, you can see that in the range of the parameter rho, for example, is restricted by A, which is basically the radius of the open ball that we introduced on initial hypersurface. And then we also have that tau is restricted by these two functions, omega and kappa. So these restriction is related to the propagation of using conformal JD6, but I'll not be going into the details of this. But the important thing that in this case, kappa is taken to be some smooth function that is of order rho, and omega is a smooth function that satisfies this condition as rho is close to 0. So basically, as we go to spatial infinity. Okay. All right. So now that I've introduced almost all of the background that I need, to talk about the conservation, I just want to recall what we have. So we had this kind of expression for the BMS-supertranslation charges, which is written, as I said, in terms of the Newman-Penrose gauge. The idea for studying the matching of these charges is that we would like to obtain their limiting behavior as we approach spatial infinity. For this, what we need basically the asymptotic behavior of the fields that appear in this expression, starting from some initial data. So in our paper, we start from this explicit asymptotically Euclidean irregular initial data, which was introduced by Lan Huang in 2010. So basically, these give you some kind of asymptotic expansion for your initial metric and for the momentum tensor. And you can see that these expressions are basically written in terms of some Cartesian coordinates on your initial slice, and they also have like these parameters. So you have like A and B. So these are some constant and some constant vector. We also have two function on the two-sphere, which is xi and zeta. Okay. Now, if we start from this initial data and we use the Friedrich's conformal field equation that I introduced earlier, we can basically obtain solutions, at least a zero-order solution for the background and the gauge fixing field, and also the gravitational field, which is in the scale is just the rescaled Weyl tensor. And similar to how we can decompose our Weyl tensor in terms of like the Newman-Penrose multitrial, we can do a similar decomposition of the rescaled Weyl tensor into like these 5 scalars, which I label from 0 to 4. Then, the thing is, like, we have our expression in this case of the BMS charges, which is written in terms of the Newman-Penrose gauge. We have our solution, but it's written in terms of this gauge, which is basically adapted to Friedrich's formulation. So, if we want to evaluate the expression of the charges, we need to basically find some kind of a transformation between these two. And, basically we find the following. So we find that in the expression of the charge, the term which is related or written in terms of the shear and then used tensor, this term goes to 0. as rho goes to 0. And then the Coulomb term, in this case, is just related to the zero order solution of phi 2. Okay, so basically, this just tell us that if we want to work with the asymptotic, with the BMS charges, and if we want to evaluate them at the critical set, this only depends on the choice of the supertranslation parameter t and the zero order solution of phi 2. Okay. Okay, so now if we do this, we find the following result. So we find that, given the initial data that I kind of introduced, the charges in general will not be well defined at the critical sets unless the initial data satisfy these following conditions, which are basically conditions that the odd harmonics of the function xi, which appear in the initial data, are vanishing. So these are obviously some restrictive conditions on the initial data. And then if you choose your initial data to satisfy this condition, we find that the charges, when you evaluate them at the critical sets, they are fully written in terms of the initial data. And from this expression, you can directly see that there is actually a relation between the charges at I plus and I minus. So basically, it's just a factor of -1 to the power of L in this case, where L is just the harmonic of the supertranslation parameter in this case. So basically the summary that at least for the initial data at hand, the matching in this case is generally not satisfied unless we fine-tune the initial data. Okay. And yeah, so this is at least the result on the BMS supertranslation charges. So I do have other part of the talk, which was related to the spin zero. I kind of might just try to speed through this, and then we can take questions after this, if that's okay or no.
Yeah, I think that sounds good. We can.
All right.
Thank you.
Okay, so yeah, as I said, so I thought, I do want to kind of just to end the talk also by giving a more explicit example, which in a setting that is a bit simpler than the full general relativity case. So as I mentioned earlier, when I first started working on the matching problem, I kind of looked at the matching for asymptotic charges for spin 1 and spin 2 field. And at the time, it was a very nice result. But in some sense, it's like the final picture is very similar to what we have in the full GR's case. So I don't want to be, going into details, but I thought it would be also more interesting to look at an even simpler model, which is the scalar field on n-dimensional Minkowski, which I studied with Edgar Gasperin and Philip Mina. And I think the reason this example is interesting because first, obviously, it's much simpler, but also, in this case, we're considering this on an n-dimensional space. So, just by considering this problem on an arbitrary dimension, we can see more clearly, whether the behavior of fields, and specifically in this case, asymptotic charge, depend on the dimension of the space. So in this, example, the setup is quite simple. You start with an n-dimensional Minkowski. You consider a scalar field tilde phi, which satisfy the wave equation. And then, in a similar spirit to what we've done in a 4-dimensional case, you introduce some cogent transformation and a conformal transformation. And this gives you the n-dimensional metric of Friedrich. And the only difference in this case is just the fact that the metric sigma here, rather than being a metric on S2, it's a metric in this case on Sn minus 2. And then you can show that this conformal transformation, basically, the one that we have introduced here, also introduce a corresponding transformation of the wave operator. And this allows us to define a conformal scalar field phi, which is related to phi tilde in this way. And since we're interested in asymptotic charges near spatial infinity, and these depend on the solution of this equation, our goal is to basically analyze the behavior of this equation near spatial infinity. So in order to do this, we consider like a formal expansion near rho equals 0 in this way, where the coefficient of the expansion in this case are decomposed into functions of the parameter of the time parameter, coordinate tau, and it's multiplied by spherical harmonics on Sn minus 2 sphere. And if you substitute this expression into your wave equation, what you get is you get basically this equation, which is a second order ODE for the coefficients of the expansion. Now, if you suppose that you start with some initial data which are kind of compatible with this expansion, so we start with this initial data for phi and phi dot, then you can find that the solution for this equation can be written in terms of these functions P and Q, which are the associated Legendre polynomial and the associated Legendre function of the second kind. And both of these equations in this case have this, their order is this nu, and it depends on the dimension of the space and also the harmonic. And from this, you can see kind of from the expression the following, that basically this order nu is an integer if and only if the space-time dimension, which is n, is an even number. And the reason this is important because you can find, or you can, just by looking at the, the asymptotics of these Legendre functions, you can find that this really depends on whether nu is an integer or not. So specifically, you can find that generically the solutions A is going to be a polyhomogeneous function. And we can only guarantee that the field is well defined at null infinity under certain conditions. And specifically, the case we're kind of interested in, at least for analyzing the asymptotic charges, is the zero order solution, which in this case corresponds to the case where you put this B to be equal to 0. And in this case, we have this table here, which just highlight how the solution of behavior at square plus and square minus depend on the dimension of the space. So specifically, for even dimension space-time, the order nu, as I said, is an integer. And in this case, the Legendre polynomial is actually a polynomial, but the Legendre function is polyhomogeneous. So in this case, if you look back at the solution, that this part is polyhomogeneous, this part is polynomial. So if we want our solution to be well-behaved, that means that we need to restrict our initial data so that this constant here is 0. Okay, so this is for the case of an integer n, u. But in the case of an odd dimension, we found that in this case, both parts of the solutions are polyhomogeneous. So that means if you try to impose initial data conditions to kill this polyhomogeneous behavior, this would basically, force the solution to vanish identically. So yeah, this is at least the summary of the solution. And then if we want to put this together in the context of, the asymptotic charges, which are associated with spin zero field, similar to kind of earlier, you can derive these charges by considering the action of Poincare transformation on the asymptotic expansion of the scalar field near infinity. And specifically, you can write these charges as, some integral over some cut of null infinity. And you have some kind of a choice of some arbitrary function of the angle, which in this case is a function on, again, Sn-2 sphere. And we also have the leading order term in the asymptotic expansion of the physical scalar field. So then in this case, if you use, we also have like a solution in this case in the conformal framework. So if you try to use the explicit solution of phi, and take the previous generic initial data condition, what you find is that the asymptotic charges are generically not going to be well defined at the critical sets unless the initial data satisfy a regularity condition. And more specifically, this behavior is really more for the case where n is an even number. But if you consider, the case for n is odd, you actually find that, there is no non-trivial charges, which would be well-defined at the critical sets, okay? So this, in a way, just show you again that, the dependence of the asymptotics basically for both the charges and for the behavior of the field, depending on the dimension of the space, okay? Okay, so I think I just will summarize. So, I will just give a summary of what we've done. So the main point, I guess, of the talk is like we've looked, as I said, on the on whether the BMS supertranslation charges are defined at personal infinity and how they can be related through spatial infinity. And in my work, this problem, we're just studying it using Friedrich's conformal framework. And, we find that basically, in this setting, that I consider the conservation of asymptotic charges across spatial infinity will not hold in generically, so that means that we cannot expect it to hold for a very large class of the spacetime, at least for the cases that I've looked at. And the reason that, this fail is because we need to impose, as I said, additional regularity condition. Okay, now the one thing I also want to note, one direction of work that I think, would be interested in pursuing after this is related to this paper, which is by Friedrich and Hanno, where they study the matching of asymptotic charges for a massless scalar field on Minkowski. And the result in this case that they have really don't match fully with what I have for the massless scalar. So specifically, the reason I think this is the case is because first they use a different definition of the asymptotic charges. And also one interesting aspect of their work is that they also allow for certain logarithmic terms to appear in the asymptotic expansion of the field. And they show that even if you have these terms, they can still formulate a Hamiltonian formulation for the asymptotic symmetry group, and you can still obtain a well-defined definition of the charges. So for me, I think this is one area that I would like to understand, at least from the conformal framework that I've been using, and specifically how these two descriptions are related, and whether we can, within Friedrich's framework, we can relax the smoothness assumption that we put from the initial data and somehow modify the definition of the asymptotic charges so that they're well-defined, even if we have some logarithmic terms. Okay? Right, so that's it.